A little while ago, Keith from New Level Auto and PJ from Voltage Drop Diagnostics YouTube channel approached me with the following question. They found out in service information for one of newer Toyota trucks that the wheel speed sensors can be directional. So they would report not just the speed, but also the direction of rotation of the wheel. And so they were wondering how the waveforms should look like for such sensors, because the regular digital two-wire sensors would report speed for sure, but there would be no information about the direction of the rotation of the wheel, just like on the following waveform. So I've tried to explore this subject and how I approached it. Well, I cannot go to dealerships and buy all possible wheel speed sensors and hope there is one that has the direction capability in it. But what I can do is go to chip vendors and see what chips they offer for the wheel speed sensors, look at the data sheets, and buy a few of them and test them out. So I found some chips that support the direction of rotation and tried to bench test them. I do not have reluctor rings, so as a crude reluctor ring I'm using a sprocket that is mounted on a ball bearing, so I can rotate it by hand, clockwise and counterclockwise. Here are the 4 sensors, and also I wound some wire on a ferrite rod to emulate the VRS style sensor. All of them are to be mounted on this PCB, connected to the battery and oscilloscope. See what the waveforms look like. Let's take a closer look at the sensors. The rightmost one is A1688, which is a 2-wire digital current signaling sensor without direction of rotation reporting. This is something that we have already explored on this channel, and I'm going to include the link to that video. But now let's just quickly recall how it works. So the sensor is connected to the voltage source and to a resistor, typically around 100 ohm. When it detects a tooth of a reluctor ring coming by, it changes the current that's passing through the sensor from 7 milliamps to 14 milliamps. This induces a corresponding change in the voltage drop on this resistor, which is then sensed by the PCM. Often manufacturers use a little bit different circuit where the resistor is located on the power side, and so the voltage drop is sensed there, which will be basically the same signal riding on something like 11 volts, just like in this waveform. This is a digital square wave, and the frequency of it is proportional to the speed of rotation of the wheel. Now let's take a look at the other 3 sensors. This one is a TLE4953C from Infineon. It's specifically designed to be used in ABS systems, and it does include the direction of rotation capability. These ones are both A1698 from Allegro, but they are 2 different variants. This is a P variant and this is a B variant. The P variant is different in that it emits pulses even when nothing is happening and the wheel is not rotating. So even if the wheel is stopped, it sends a signal, I'm here, and depending on the pulse width, it can tell everything is alright, I'm alive, or it can say something is wrong. The B variant is silent at a standstill and starts to emit pulses only when the wheel starts to move. The circuits for all these 4 sensors are exactly the same. All you need to do is to add a resistor, about 100 ohm, and connect it to the power source, and connect the lead of an oscilloscope to check the signal. So why don't we just do exactly just that, and get our soldering iron and put all of them on the PCB so that they face the teeth of our improvised reluctor ring. I know it's a crude setup, but oh well, it's the fastest that I could come up with, and see how well they work. Just, add battery and an oscilloscope. And the funny thing is, if we do that, nothing will happen. It will not work. We won't get any signal on any of those 5 sensors. It is because we are missing something. Missing something crucial. Can you guess what it is? Okay, so what are we missing? Well, all these sensors react to the change in the magnetic field. But our reluctor ring is just a chunk of metal. Even if it spins, there is no change in the magnetic field. So for the sensors to become useful, we need to provide an external magnetic field, and the rotating reluctor ring will change it. So then sensors can detect it. Thus, we need to provide something called a back-biasing magnet, just like in the pictures provided with the datasheet for, let's say, A1698. So we have a reluctor ring with teeth, and we need to have a back-biasing magnet. So not only we need to mount the sensors on the PCB, we need to put some magnets behind them. So I went to a box of random things and fished out some magnets out of there. They are kind of big compared to the sensors, but this is what I have, and this will have to do. One other question you might have is that we have 5 sensors in total, and 5 signals would be too many for a 4-channel oscilloscope. But I have a secret weapon, Pico MSO. MSO standing for Mixed Signal Oscilloscope. It has 2 analog channels and 16 digital ones. So I'm going to connect VRS sensor to channel A, TLE sensor to channel B, so that I can see the levels produced by the sensor. But then all 4 digital sensors I'm going to connect to digital channels D0, D1, D2, D3, so that I can see when they switch from low to high, and I'll be done. I'll have all the signals on the oscilloscope waveform at once. So let's see how it looks like. So here we have the whole rigmarole with the Pico MSO on the left, battery connected, all the sensors with back biased by magnets, reluctor ring, and also from another angle, this is how we have it. And so without further ado, let's spin the reluctor ring and see what we have on the waveform. And here it is. We have VRS sensor on channel A, TLE sensor on channel B, also on channel D1. D0 is the regular two-wire digital sensor, so we can see that it reports the speed using the digital square wave. But for D1, D2, D3, we see quite a different picture. This is just a collection of very, very short pulses, and actually the picoscope program, when plotting them, misses some of them at such zoom level. So we have to actually zoom in to see what's going on. But first, notice that for the A1698P version of the sensor, it emits signals even when nothing is happening. So let's zoom in on this standstill pulse and see what it looks like. It is 1.4 milliseconds, and basically that the sensor is saying, I'm alive, everything okay, but nothing is moving. Now let's zoom in into the region where we started to rotate the reluctor wing in one of the directions. So we see some sort of a sine wave on the VRS sensor, and the TLE sensor reports the same speed using the pulses, and those pulses are very, very short. So we'll zoom in, way in, and measure them. And they are, in our case, about 60 microseconds. This is how short they are. And the same thing happens to the other sensors, only they're using slightly different pulse length. Instead of 60 microseconds, it is 90. And this is what happens when we rotate the reluctor ring in one direction. Here on the waveform, I flip the direction of rotation, so we can see that at this zoom level, we still see the pulses, but the pulse width has changed now. Let's measure it. Now it's 120 microseconds for the TLE sensor. And what is it for the other sensors? Here we can see that the other sensors also have changed the pulse width to 180 microseconds. So here you go. We have the sensors reporting pulses this time. And one thing that is very interesting is that you see that the regular sensor reports a digital square wave, high, low, and the TLE sensor basically reports the pulse once per period, while the other two sensors report it twice, both on the rising edge and the falling edge. It's just how these sensors work. It's written in the datasheet that they will produce two pulses instead of one, and when the manufacturers are processing the signals, they basically have to know how these sensors report the speed and direction. And this can be very confusing if you are seeing these waveforms for the first time, because at first they do not really make any sense. And a nightmare can happen if, for example, you got a sensor that is very similar but from a slightly different manufacturer, or a different even version of the sensor. Like I said, this D2 and D3 are only different that at a standstill this one emits extra pulse. If a wrong type of sensor is being used, the PCM will go bananas and will say it's no good, and it will be really hard to understand what it doesn't like. So you will have to go to another wheel that you know is working and collect such a waveform with an oscilloscope that has a very good sampling speed. Look here, I'm collecting at 300 kilosamples per second. So if you're using something like a muscope, you might miss such short pulse, because the pulses can be anywhere from 30 microseconds and up, and so if the sampling rate is not big enough, you might just miss the signal. And so you will have to go and compare whether you are getting the same type of signals on a known good wheel and on a suspect wheel. You will have to compare the pulse width, whether you are having pulses at a standstill, and only then you will be sure whether you diagnosed that sensor correctly or not. And so this is it about the three sensors that can detect the direction of rotation of a wheel. They are straightforward generalization of the regular digital sensor. They're using pulse width modulation to report the direction of a wheel. They use exactly the same circuits as the regular digital sensors, but using an oscilloscope to diagnose them is harder just because the pulse width is so small, somewhere between 30 to 180 microseconds typically. And this is not it. There are some even more complicated sensors that use something called AK protocol, which is much more complicated, and basically it goes like that. After each speed pulse, you would have a whole byte of data encoded that has a lot of stuff in there: direction, air gap, and some other diagnostic values. And we are not going to talk about those today. Maybe if someone encounters them in real life and posts a waveform, then I will cover them. But this is it for now. Any questions and concerns, and anything that you would like to add to the discussion, please do that in the comment box below, and see you next time.